Hello, I'm Yasir Nawaz. Today I will present some mathematical model of spring mass system, and I will try to solve the equation using Laplace transform. So here on the board, I brought a picture. So in picture, the first picture shows the spring, just spring, and there is no mass which is attached with this spring. In the second picture, the mass is attached with the spring, and the system is in equilibrium. The one force is acting is W is equal to mg. Other force is acting F is equal to minus K. F is equal to minus Ks. So both forces balances each other. And the third situation is this when there is a motion. So in motion, it stretches the spring by the length of L S plus X. So now according to Newton's second law, um, F is equal to ma. So m is the mass and a is the acceleration. So that can be written as t square, this length. This uh, the length can be written as x over dt square. So that's because of Newton's second law, and I write it in the form t square x dt square, and then the downward force is W is equal to mg. One force is mg, and then according to Hooke's law, so the other force will be S plus X. Now this can be written as mg minus Ks minus xk. So now because due to the equilibrium, mg minus ks is equal to 0. This thing becomes 0, so the remaining would be kx. So m into. So also remember that here this is the case when there is no damping. There is If there is a damping, then the damping force will be added. So here the case is discussing where there is no damping. So it's the case for undamped system. So using the Newton law and using the Hooke law, the model is constructed in this way. Now, if the damping force is applied, if some damping force is applied, then the equation can be written as, then the damping would be, it can be written as m d square x dt square plus some constant into the velocity. The velocity can be written as dx by dt and then plus kx. So these are the two different situations. The one situation, this equation deal with the mass is a mathematical model for the mass spring system and with no damping. And the second equation represent the mathematical model for mass spring system with damping. Now, now I will try to add some external force. Suppose that I start with the unit step function. So unit step function, uh, I draw its graph. It's a bit, suppose that this is the x-axis or t-axis, this is the y-axis or u-axis. So here, it if when the value, so unit step, I'm talking about u of t, the unit step function where t is the independent variable. So when t is less than 0, when t is less than 0, u of t is 0. U of t is 0 when t is less than 0. And when t is greater than 0, when t is greater than 0, ut would be 1. So here, the one force here, this is 0. and this is 1. So that's a unit step function. If I apply the translation in this unit step function, so the translation suppose that I apply, I write it as ut minus 1. So ut minus 1, so this whole function will be translated 1 unit right. So now it becomes in this way, and then here in this way. So it is 0 here, and it is 1 here. So you can also add this vertical line. So that's a translated unit step function. So which is translated towards positive x-axis with the step of 1. So here this is the universal. Now if I use ut minus 1 and minus ut minus 2, what is meant by that? Ut minus 1 and then ut minus 2. So these are the two function. One is translated 1 unit right, other is reflected and also translated because this minus sign before you, this minus sign is due to the reflection. So it's a reflection and translation. So the whole function would become, I suppose that at 1 and 2, it gives the value 1. At 1 and 2, at 1 and 2, it gives the value 1. And then the rest of t values, it gives the answer 0. So it's 0 here and 1 here between 1 and 2 and 0 elsewhere. So these are square wave. So I discussed the problem with the where the external force is square wave. Suppose that the example is this one. This is the example. This is the example. In this example, second order ordinary differential equation, you can see on the left side there is a mass. The equation that can represent the mass spring system. On the right side, the force external force is applied in the in form of square wave. So ut minus 1 is actually a translated unit step function, and minus ut minus 2 is the reflected and translated unit step function. So I will try to, and the initial condition are also given y of 0. Y of 0 is 0 and y prime of 0 is equal to 0. So now I will try to apply the Laplace transform on it. So when I apply the Laplace transform on both sides, Laplace transform will be applied on this term, on the whole left hand side, and also Laplace transform will be applied on the right hand side as well. So on the left side, the derivative of y double prime, that the formula will be used for the Laplace transform. So it can be a ys. Ys is actually Laplace transform of yt. So y of s is the Laplace transform of yt. Then s y of 0 minus y prime of 0. That's a Laplace transform of second derivative. Now the Laplace transform of first derivative would be 3s into y of s minus 3 into y of 0, and then plus 2 Laplace transform of y. Laplace transform of y would be y of s. So these three terms are the Laplace transform of y double prime. These two terms or the Laplace transform of 3y prime, and the last term represents the Laplace transform of plus 2y. And now the Laplace transform of unit step function. What is the Laplace transform of unit step function? So here that Laplace transform of unit step function, suppose that if it is ut minus 1 and there is some other function f of t, so its Laplace transform would be, what would be the Laplace transform for this case? It's e to the power minus s and Laplace transform of f of s, f of t, which is f of s. So this is the property which can be used. So here f of t is 1. Here is 1. Here is 1. F of t is 1. So if I apply the Laplace transform, so I will get e power minus s. Laplace transform 1 is 1 over s. So it's 1 over s. And then minus e power minus 2, e power minus 2s. And Laplace transform of, and then 1 is 1 over s, which can be written as 1 over s, and then e power minus s, and then minus e power minus 2s. No, I apply the initial condition because y0 is 0. So y0 is 0, so this term would become 0. Y prime is also 0. So this would be 0, this would be 0. So these term would become 0. The rest of the term can be written as s square y of s, and then plus 3s y of s, and then plus 2 y of s is equal to 1 over s, 1 over s e power minus s, e power minus s minus e power minus 2s. So because y of s is present in each term, so I write y of s outside, and then inside there would be s square plus 3s plus 2 is equal to 1 over s, 1 over s, and e power minus s, and e power minus 2s. So this thing. Now I bring this thing on the right hand side. So y of s is equal to 1 over s, 1 over s square plus 3s plus 2. And this thing is e power minus s minus e power minus 2s. So here this thing can be factorized, and the factor of these would be using the midterm break. So that the factors are s plus 1 and s plus 2. So here you have to find, so because when you multiply 1 with 2, you will get 2. So 2 into s and s into 1 would be s. So 2 plus 1 would be 3, so 3s. And then s into s square. So you will get that. If you cannot write the direct factor, so you can in some other place, or so you can factorize it, and when you will factorize it, you will get these two factors. So I'm not going into that factorization thing. So this thing. No, I will apply the Laplace inverse. When I will apply the Laplace inverse, so these are the three factors which are multiplying with each other. So what I will do, I will try to use the partial fraction for this thing. If I use a partial fraction for this thing, so it can be written as 1 over s plus 1, sorry, 1 over s, and then s plus 1 and s plus 2. So these can be written as I write these thing directly. So these would be 1 by 2 over s, 1 by 2 over s, and then minus 1 by 1 by s, 1 over s plus 1, and then the last term is half over s plus 2. Now I find the Laplace inverse of this Laplace inverse. Here I apply the Laplace inverse, and not the next step I write this thing. So I apply the Laplace inverse on this side. This side is 1 over s into s into s plus 1 into s plus 2. So here I apply the Laplace inverse. The Laplace inverse I apply, so I write 1 over 2 over s, and then minus Laplace inverse 1 over 1 over s plus 1, and then plus 1 over 2 Laplace inverse of 1 over s plus 2. So here I bring 1 over 2 outside. So Laplace inverse of 1 over s is 1. Laplace inverse of 1 over s plus 1 would be minus e power minus t. And here that would be e power minus 2t. So that's a Laplace inverse of this thing. So actual function is this one. This thing suppose that this that the quantity inside these brackets that can be represented as f of s. Suppose that this is f of s, and that's a Laplace inverse. So Laplace inverse will apply on f of s, and it will give this thing. Suppose that this thing is small f of t. No, the task was to find the Laplace inverse of this whole thing, not just this function f of s, but it is actually it's an inverse of whole thing. To find the Laplace transform of whole thing, so it's a Laplace inverse 1 over s into s plus 1 into s plus 2. So here if I write e power minus s, so its Laplace would be it's a e power, it's a unit step function u t minus 1. Because of this e power minus s, its Laplace would be ut minus 1, and then Laplace transform form of Laplace inverse of f of s. Laplace inverse of f of s. The Laplace inverse of f of s would be, so that can be written as u. No, it would not be f of s just. It would be a f of t minus 1. F of t minus 1. These are Laplace inverse. So similarly, I will find the Laplace inverse for the second quantity. So a Laplace inverse of e power minus 2s. So its Laplace inverse would be s. No, 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 not Laplace inverse. First I write this thing s into s plus 1. Please consider my words only for this topic, not for any other. So here, Laplace inverse of this whole thing would be u t minus 2 and then f of t minus 2. So that's a Laplace transform for the second one. So now I will write it as, so here the ys on the left side, if I use the Laplace, on the left hand side, I apply the Laplace inverse. On the left side, if I apply the Laplace inverse, so that would be Laplace inverse of ys and then Laplace inverse of y over 1 over s into s plus 1 and then s plus 2 and then in the bracket it was e power minus s and then e power minus. So this thing so here the first thing is becomes ut minus 1 f of t minus 1 and then minus ut minus 2 f of t minus 2. So that's answer that can be written into some other form. So when t is less than 1, when t is less than 1, ut minus 1 would become 0. So this thing would become 0 and this thing would also become 0. This thing is 0, this thing is 0, both will be 0. When t is between 1 and 2, then uh, uh, when t lies between 1 and 2, so this would become this will give 1 and this will give 0. So in that case, f of t minus 1. And then when t is greater than 2, so this will give 1, this will give 1. So and that the answer would be f of t minus 1 minus f of t minus 2. So that's Laplace transform of ordinary differential equation with uh, the external power, with the external force is in the form of unit step function or you can say square wave. So it's a Laplace transform of Laplace transform of this particular situation, the mass spring system, in which external force is in the square wave. I present one more example. That's a impulse function. So impulse actually is a force uh, that becomes the area of some particular region. So that becomes the impulse. So impulse is actually what is this thing? It's suppose that there is a square. So one, this is A and this is A plus K. So it's a square wave. So here this thing, and then it is zero here and it is zero here. When and suppose that so this length is K, this length is K, and suppose that this length is 1 over K. Actually, when the limit will be applied, K approaches to 0, these two points, this point will approach to this point, and because the area should be 1, so this length approaches to infinity. This point will goes to the K would when the K would become when K becomes 0, the height of this rectangle will approach to infinity. So area still will remain 1. So that is called the unit impulse. So for handling this kind of equation, I apply the Laplace transform. If I apply the Laplace transform, similarly as in the previous part, so Laplace transform would be S. I do not write all the steps. I just write S into S plus 1 and S plus 2. S plus 1 and S plus 2. The Laplace transform of delta t minus 1 to t would be e power minus t. Oh, sorry, not minus t because it will convert into the S form. So e power minus S. Here I write one more thing. So y of S. Variable y, so it's a y of S. Now y of S would be e power minus S, e power minus S over S into S plus 1 and S plus 2. And now this can be written as, so after using the partial fraction, so it can be written as 1 over 2 over S minus 1 over S plus 1 and then plus 1 over 2 S plus 2. 1 over 2 S plus 2 and then here that would be e power minus S. Now when the inverse Laplace transform will be taken, so what would happen? Uh, y double here it is y double plus 3 y prime plus 2. Okay, if I write into this form, so y of S is this one. So now y of t, I use the same initial condition for as I used in the previous example. So y of t would be, so that would become, so it was actually becomes uh, f of t. What is f of t? F of t is the Laplace inverse. F of t is the Laplace inverse of this thing. And Laplace inverse of this thing would be 1 over 2 minus e power minus t and plus 1 over 2 e power minus 2t. So here it become q minus 1 and f of t minus 1. So that is the answer for this situation. Okay, I end this video at this moment. And so, bye.